Hello everybody, and welcome to this webinar on Advanced Elemental Analysis of Semiconductors and Microelectronics using QUANTAX WDS for SEM by Bruker. My name is Max Bugler. I'm an application specialist for microXRF at Bruker Nano Analytics in Berlin, and I will be the host for this session. Before we start, let me give you some housekeeping details. You should at this time be seeing the introductory slide on your screen. This webinar is an interactive webinar. You can ask questions at any time during the presentation by entering your question in the recording box on the right-hand side of your screen and sending them to us. The presentation will last about 45 minutes. We have two short videos on how to collect data towards the end. And after the presentation, I will present your questions to the speaker. If we are not able to get to your question during this live event, we will follow up with you by email. Be aware this webinar is also being recorded and will be available as on-demand version very soon. So let's get started, and let me first introduce our speaker. Our main speaker today is Dr. Michael Abrates. Michael studied geology at the universities of Kiel and Göttingen, where he also acquired his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michael built up and managed a microprobe lab at the University of Jena before he joined Bruker Nano Analytics as a senior application scientist for WDS in 2015. Our second speaker is myself. I studied physics at the Berlin Institute of Technology, also known as the Technical University Berlin, with a focus on optical spectroscopy and thin-film semiconductor materials. I went on to Georgia State University in the US for my PhD on the epitaxial growth of 3,5 nitride semiconductors and their characterization. After a few years as a scientific consultant in different parts of the world, I joined Bruker's microXRF team in 2015. So just let's get started, and let me pass over to Michael.
Thank you very much for the introduction, Max. Thank you. Hello also from my side here. I'm Michael. Today we will focus on the analysis of semiconductors and related microelectronics. In this webinar, we present results from the analysis of molybdenum disulfide, tungsten silicide, tantalum silicide, and silver-doped lead telluride with bismuth segregations. You can see the sample here. The bright phases are the segregations. Furthermore, we will have a look on a layered sample made of tungsten, tantalum, and silicon, and we will investigate a MOSFET structure from a semiconductor microchip. Why should we use WDS for SEM when investigating semiconductors and related microelectronics? High spectral resolution, or high energy resolution, is one of the primary arguments for the deployment of WDS in X-ray microanalysis. The limited spectral resolution of EDS frequently causes serious peak overlap problems. These peak overlaps are common in many semiconductors, as we will see in the following slides. EDS tackles this problem by using peak deconvolution. WDS instead can resolve many of these overlaps. WDS thus needs no post-processing of the data such as deconvolution. WDS can achieve a higher precision in element identification and quantification. Since many structures in semiconductors and microelectronics are very small, a high spatial resolution of the analysis is required. To achieve this, low voltage has to be applied to the analysis. And that in turn requires the ability of high spectral resolution at low X-ray energies. The QUANTAX WDS for SEM is ideal for applications like these. Today's webinar will be structured like this. The presentation is basically divided into 6 sections. The first part will give a short introduction to the QUANTAX WDS system and provide some details about the spectrometer hardware, its working principle, and main features, including the advantages when compared to EDS. In the second part, we will provide some background knowledge on semiconductors. After that, we will show application examples on semiconductors as well as on a few samples of semiconductor microchips. Towards the end, you will see 2 short videos on the workflow of WDS analysis, before we then conclude with a summary of the WDS benefits. The QUANTAX WDS is an integral part of the QUANTAX family of devices for SEM-based microanalysis. The X-sense spectrometer, as the main component, is a so-called parallel beam spectrometer with a grazing incidence optic here on the tip, which can be also retracted. The QUANTAX WDS is fully integrated in our software package S32. So everything is within one software, EDS, WDS, and all the other devices. This slide here shows the setup and working principle of the X-sense spectrometer. The parallel beam optic is positioned pretty close to the sample, and thus captures a large effective solid angle. So we've seen the optic, which is a very important part in this parallel beam spectrometer, is close to the sample, so we capture X-rays with a high effective solid angle. The resulting X-ray beam is parallel, and this parallel beam hits one of the flat crystals here where Bragg diffraction occurs. Here are up to 6 crystals on the turret. Only photons of certain energy fulfilling the Bragg conditions are reflected towards the proportional counter, which is used for X-ray detection. According to the Bragg equation, the energy, or the wavelength lambda, of these photons is a function of the adjustable Bragg angle theta, which is the incidence angle of the beam relative to the crystal surface. Theta is given here. This is the incidence angle between the crystal and the X-ray beam. And the second parameter is the lattice constant D of the analyzing crystal. Basically, this setup describes an X-ray monochromator, which is very narrow band and hence capable of delivering high spectral resolution. So we are filtering out all the X-rays. We get only one monochromatic X-ray, but intensified due to constructive interference. As WDS and EDS actually measure the same physical property, it is important at this point to realize that there are some main differences between the two techniques. These are, first, a substantially higher spectral resolution of WDS compared with EDS. Typical values are in the 3 to 15 electron volts range. So that means 10 to 20 times better than EDS. Second, enhanced peak-to-background ratios, which translates into lower limits of detection, up to about 100 ppm. And third, this is a special property of the parallel beam spectrometer with the grazing incidence optic, outstanding light element sensitivity. With these properties, a WDS can be an ideal complement to an EDS system in demanding applications where EDS peak overlaps are an issue, when trace element or light element detection capabilities play an important role, or for low kV applications if high spatial resolutions are desired. Semiconductors are such demanding applications where the QUANTAX WDS can be of great help. And with this, I hand back over to Max, who will give us an introduction to semiconductors. Max, please go ahead.
Thank you, Michael. First of all, I just want to give a very, very brief introduction here. What is a semiconductor? If we just look up in Wikipedia, a semiconductor material has an electrical conductivity value falling between that of a conductor, such as metallic copper, and an insulator, such as glass. That seems a very straightforward separation. And how can we describe this in terms of physics? Usually this is depicted through the band structure, and the band structure describes the energetic position of the so-called valence band, where electrons are situated that are very tight to the atoms, and that basically can not conduct a current. And the other important band is the so-called conduction band, where electrons now can potentially hop from one to another atom and thus contribute to carrying a current through a material. And that is usually described by the Fermi level, which I'll describe a little more in detail on the next slide. So on the left-hand side, you see in a conductor, those bands are usually in contact or actually overlapping. So there's always carriers available that can carry a current. On the other end, we have an insulator. In an insulator, there's a large gap between those bands, so it needs a certain amount of energy to bring an electron from the valence band into the conduction band, and this is basically insulating at normal conditions up to a certain breakthrough voltage or very extreme conditions. But in between, we find now the semiconductor, where those bands are still separated, but are close enough to each other so that with typical photon energies of visible light or with thermal excitation, we can generate now carriers that can carry a current, and as well we will generate holes in the valence band that can as well contribute to the current by basically respectively being filled from neighbors and thus moving in the opposite direction of the electrons in our material. And on the next slide, we see here now the Fermi level describes the energy at which there is a 50% probability of a virtual state to be occupied at the given conditions and under thermal equilibrium. So on the left-hand side here, we see this Fermi level in an undoped intrinsic semiconductor is right in the middle between our valence and the conduction band. In an insulator, we would see a similar situation. Now, what makes semiconductors such an interesting material is that we can, by doping, generate so-called p-type or n-type doping. So we generate additional holes or additional electrons by putting atoms of a different species or defects into our semiconductor. And with this, we can tune the probabilities somewhat. The whole behavior can be described by the Fermi-Dirac equation. And in that Fermi-Dirac equation, we see there is a temperature dependency. We have the Boltzmann constant times the temperature in the exponent, or actually, anyway. So what we see here is that with changing temperature, we will change the distribution of electrons. So we can actually, due to temperature, increase the conductivity. And if we cool it down to zero and have an undoped semiconductor, we would find that there's almost no conductivity left. This Fermi level can also be shifted not only by incorporating those so-called donors and acceptors, but by external fields. So in certain geometries, we can now control current through a device, and those properties altogether make the semiconductor materials very interesting for building amplifiers, rectifiers, and potentially light emitters and detectors. And so on the next slide, I will show you a few possibilities what we can do with it and what has typically been done. So resulting from that temperature dependency of the conductivity, it allows for the construction of thermocouples or thermometer devices with a very high sensitivity in certain temperature ranges. On the right-hand side, we see here different germanium materials in a thermocouple setup. And on the one hand, we can see the resistance as a function of temperature, but more interestingly, to compare it with a classical thermocouple would be the sensitivity, which is the second plot on the right, where we can see now that by changing the doping of our germanium crystal, we can basically tune the sensitivity range over about 300K range, 400K, and therefore we can build temperature gauges which are very sensitive for specific ranges and have a superior sensitivity in those ranges. As a second application, these carriers can be generated by absorption of photons of light of a sufficient energy. And so they are very useful for photodetectors. And as we can tune the band gap, we can make now photodetectors that are only sensitive for UV, or we can optimize them to be sensitive in the infrared range. So it allows us to have photodetectors that count as many photons as possible without having a filter in front of them to shift the sensitivity into a certain spectral region. In certain semiconductors with a suitable band structure, so mostly direct bandgap materials, as well the reverse effect is possible. So we can basically pump electrons and holes into a material, and as they relax and jump across the bandgap, the energy difference is released as photons, and we can generate basically light emitters, classic LEDs, or even laser diodes. And we see here on the right-hand side the blue light out of an indium gallium nitride LED, and as well the band structure of gallium nitride, where we can see that at the gamma point in the center of the plot, the maximum of the valence band and the minimum of the conduction band are in K-space at the same position. And therefore, for this transition, we don't need any momentum from the lattice, and this allows us at low and high temperatures still to have very efficient recombinations, whereas in an indirect band gap, we would always need the assistance of phonons out of the crystal in order to allow those transitions. Last but not least, if we combine different doped areas of a semiconductor or even different semiconductors, we can build now diodes where basically we only allow current in one direction. And if we put two of those together as depicted on the right-hand side, we can build actually a transistor where we can now control a current through that device by a voltage that we put on the gate B, and basically control with that the overall current going from E to C through our device here. And the combination of those two allows now for building complex logic structures, fast amplifiers for signals, and things like that. And what Michael will later show is that basically we can grow those in an epitaxial way, so the whole structure would be flipped by 90 degrees, and by lithography and etching process, we can now structure those, and that enables us to build processors with tens or hundreds of thousands of individual logic switches on a very small area. And with that, I would hand back to Michael to continue on the investigated materials here.
Thank you very much, Max, for the interesting lecture on semiconductors. Our first application example will be molybdenum disulfide, or also called molybdenite. The BSE image that we see here shows platy band crystals. Bulk molybdenum disulfide is a diamagnetic indirect bandgap semiconductor similar to silicon with a bandgap of 1.23 electron volts, while molybdenum disulfide monolayers have a direct 1.8 electron volts electronic bandgap supporting switchable transistors and photodetectors. Molybdenum disulfide shows a really strong pathological EDS peak overlap between molybdenum L and sulfur K lines. The energy difference between sulfur K alpha and molybdenum L alpha is only 14 electron volts. This clearly cannot be resolved by EDS. The peaks are too close together. On the left, you see the entire spectrum acquired at 10 kilovolts acceleration volt, and in the right-hand side diagram, you see a blow-up of the region of interest with the interference of the molybdenum L lines with the sulfur K lines. However, EDS has a great tool, which is called peak deconvolution. The actual measured spectrum is modeled by fitting the peaks with pure elements. There are several models available based on theoretical or measured profiles, single line or line series fits, and different fitting algorithms. Peak deconvolution can solve overlap issues in most cases. On the upper left side, you see fitting of these molybdenum and sulfur overlaps. WDS instead resolves X-ray peaks. With a 13 times better resolution than the best EDS, QUANTAX WDS can separate, means resolve, the molybdenum and sulfur peaks from each other. The diagram on the lower right shows the WDS spectrum, which is actually an energy range scan, in comparison with the respective EDS spectrum section. So you can see in the graph the peaks are intergrowing, but still you can nicely separate the molybdenum L alpha from the sulfur K alpha, and you can also see the molybdenum L beta peak and the sulfur K beta peak. So this is nice resolution. It should be mentioned at this point that resolution of the X-SEM spectrometer with its grazing incidence optic is better than that of any WDS using a polycapillary lens. The second sample is tungsten silicide. The electrically conductive ceramic material tungsten silicide is used in microelectronics such as microchips. The present sample, which we analyzed, is granular with particles of about 10 micrometer in diameter. The red square here in the more or less in the center of the image indicates the mapping area, which we see in the next slide. In one of the next slides, sorry. At first here we see some point analysis. Here's an EDS spectrum of tungsten silicide acquired at 20 kilovolts, showing the pathological peak overlap between silicon K lines and tungsten M lines. The close-up of the upper left shows the EDS peak deconvolution model. So fitting of the tungsten and silicon element peaks into the measured spectrum. Here we see WDS. The respective energy range scan is shown in the diagram on the right-hand side. WDS clearly resolves the silicon K and tungsten M lines. Resolution of silicon K is 20 times better by WDS than by EDS. Deconvolution is thus not necessary for WDS. The single peaks are nicely separated. Now we get to the close-up here. This is a close-up on the same sample, and in this close-up we did some WDS and EDS mapping to test for sample homogeneity. You already see different gray scales, different gray scales in the BSE image, which imply different composition of the material. So homogeneity is not true. EDS and WDS are always acquired at the same time, so that we can directly compare results gained under identical conditions. We see here or we will see mappings in the following. We start with EDS mapping. So this first row shows the raw data of EDS mapping. Silicon, tungsten, and a combination of both elements with and without BSE are shown here in this row. We see silicon in red and tungsten in blue, and we see that there's some difference in respect of the silicon content. Two particles are obviously somewhat different in composition from the rest. They clearly seem to be higher in silicon content. Here we see the result of EDS deconvolution. Deconvolution suggests that many particles have a low silicon content, except for the two particles, but all particles have tungsten, also the two silicon-rich particles. Now we compare with WDS mapping. WDS mapping shows variations in the silicon content and gives evidence that the two particles contain no tungsten. You can see that in the blue graph. The two particles are missing any blue color, so there is no tungsten in these particles. And actually, it should be like this. The two particles are actually pure silicon chips in the sample, which do not contain any tungsten. And the majority of the particles surrounding these they are tungsten silicide. So in conclusion, WDS mapping better images the element content and relative proportions. The next sample is tantalum silicide. Tantalum silicide is used for oxidation or temperature-resistant coatings in microelectronics and in optics. The present sample is also granular, with particles of more or less 10 micrometers in diameter. The red square on the right side indicates the mapping area that we see in one of the next slides. So we map a single grain. At first, we have a look on a spectrum from a point analysis. Tantalum silicide shows a pathological EDS peak overlap between the tantalum M lines and the silicon K lines. These lines are only 27 electron volts apart and cannot be resolved by EDS, but they can be deconvolved. So here we see the result for EDS peak deconvolution as well as for WDS peak resolution on the lower right. The energy range scan is shown in the graph of the lower right, and there you can see that WDS nicely resolves the single peaks of silicon and tantalum. These images, SEM images, SE image to the left and BSE image to the right, is showing the single grain that we mapped in the following. Similar to the preceding sample, the tungsten silicide is from a set of standards. A standard should by definition be homogeneous. However, a close-up indicates that this is obviously not the case. We clearly see darker areas and bright inclusions here within the single grain, the single particle. This is clearly indicated in the BSE image here, darker inclusions and brighter inclusions. We acquired EDS and WDS maps on the present particle labeled as tungsten silicide. And this first row of maps shows the EDS maps, the results of EDS mapping for silicon, tantalum, and a combination of both elements compared with the BSE image. What we see is distinct heterogeneity of this sample that is even worse than what we expected from the BSE image. The patchy pattern is actually not matching with the BSE image. We see here much more heterogeneity in in silicon and tantalum, and the combination, what we cannot see in the BSE image. Note that silicon and tantalum element distribution are supposedly the same. EDS deconvolution results in a quite different picture for tantalum. You see here the differences. We see local enrichment matching the BSE image. So enrichment where we see the bright spot in BSE. WDS shows more variation in tantalum content than what EDS implied. So here we see not only the bright spots, but we see also differences in this area between somewhat lighter and darker areas. Furthermore, the silicon variation is more pronounced. So there's more contrast between the different areas. In conclusion, WDS provides more detailed information on sample heterogeneity. Here's a compilation of the result. Here's a WDS map for silicon and tantalum distribution in the sample. Besides tantalum disilicide, marked here with yellow here, the areas of tantalum disilicide, what the sample is characterized as here, tantalum disilicide. There are also areas, we also find areas of tantalum silicide which is enriched in other elements such as iron and nickels. These are the olive green areas. And we see furthermore inclusions of pure tantalum, the bright spots here, and inclusions of silicon, the dark red spots here, or red-brown spots. Now we have a look on a fourth sample. Another semiconductor sample with an interesting structure is the silver-doped lead telluride. The BSE image nicely shows the hexagonal crystals. So you see here the hexagons nicely here as well. So everywhere hexagonal crystals, which are cut perpendicular to their length axis. The crystals are surrounded by a braid segregation phase. Here you see the segregation phase with a high density, obviously. Here are the results from EDS mapping with automatic element identification. Lead and blue, tellurium, lead in red, tellurium in blue, and silver in light blue are readily identified in the sample. At first glance on the maps, some spectrum identification of the elements seems to be complete. So it seems that the spectrum is well matched with the fitting, but this is only at first glance. Since we definitely see that some areas are not showing any colors. We clearly see that the segregation zones here in this color shown in black, and here with the map and BSE overlay shown in light in white. They show no colors in the mapping. Elements are obviously not identified in these regions. In order to identify the missing elements, there are several options available, such as first extracting an object spectrum from the area of interest, so extracting a spectrum from the segregation zones. Second, investigating the map sum spectrum. This is what we did here. This is a close-up from the map sum spectrum. investigating it in detail with the finder function. So there's some misfit here. Some element is missing, and the finder will tell you what it is. And the third option is creating a maximum pixel spectrum, a synthetic spectrum of the maximum intensity of each channel and each pixel. And this maximum pixel spectrum is then, or the auto ID function is then applied to this synthetic spectrum. And all these options indicated Wismut VI as the most probable missing element. To test for this, to test for the Wismut indication by EDS, we used WDS and gained overwhelming evidence. So we set the system to Wismut line, mapped for Wismut, and found Wismut everywhere in the segregation areas surrounding the crystals. And yeah, you can nicely see this here in the WDS map. WDS energy range scans acquired on the segregation zones nicely show distinct Wismut lines. Here, these are the Wismut peaks of the Wismut M lines, whereas energy range scans acquired on the crystals don't show these Wismut peaks, but distinct peaks for the lead M lines. So lead is indicated in the crystals and Wismut in the segregation zones. Short excursion before we continue with application on microelectronic samples. The majority of EDS peak overlaps is found at relatively low X-ray energies. Peaks are better separated at higher energies, and furthermore, including higher energy lines in the deconvolution models also facilitates deconvolution of the respective low energy peaks. So why wouldn't we thus apply or always apply high voltage for the analysis? The answer is simply spatial resolution or depth resolution. So with too high acceleration voltage, we are losing resolution. As you know, the primary electron beam energy determines the excitation volume in your sample. The higher the primary energy, the larger the interaction volume in your sample material. Here's a Monte Carlo simulation of this effect, and this nicely shows the increase of the interaction volume with increasing acceleration voltage. In this case, we have investigated a layered system with two different sulfides. The actual electron penetration depth in the investigated material also depends on the composition of the sample. Here is a sample to investigate the primary energy effects on depth resolution. It is a layered structure. On the sample, there are several layers, layered structures composed of 20 nanometer thick, or I should say thin, layer of tungsten. Sorry, tungsten is here on the right side always. The tungsten layer on top of a tantalum layer, which are both on top of silicon substrate, indicated by the dark colors here. The red square indicates the mapping area in one of the following slides. At first, we see results of point analysis. We made an analysis here right in the center where the two layers are overlapping. The slide shows two WDS energy range scans, one here, one there, along with the EDS spectrum section acquired at different acceleration voltages. To the left, acquired at 20 kV, and to the right, acquired at 5 kV. The spectra indicate the electron interaction depth in the layered sample. At 20 keV, there is a high proportion of the substrate in the analysis, indicated by the dominant silicon peak here in the center, and only minor contribution from the top layers, tantalum and tungsten. The analysis at 5 kilovolts instead gives considerably more information from the top layers. Tantalum here in green, marked in green, and especially tungsten, marked here in violet colors. The tungsten peaks are prominent. It can even be derived that tungsten makes up the uppermost layer succeeded by tungsten here, succeeded by tantalum on the silicon substrate. Tungsten, tantalum, and all this is on the silicon substrate. Now we have a look on mapping results. Here are the element distribution mappings of the layered sample captured by EDS. Raw EDS data implies that silicon, tantalum, and tungsten are always enriched in the same place. So highest contents are obviously found here in the area surrounding the layers. EDS deconvolution gives a more clear picture. It indicates roughly the distribution of silicon and tungsten. Tungsten makes up the layer on the right, which is actually matching what we expect. Whereas silicon is best seen in the areas surrounding the layers, so not covered by the layers of tantalum and tungsten. The tantalum content seems to be highest in the center, which is somewhat implausible. Here we see the results of WDS mapping. WDS shows the correct distribution. Tungsten makes up the layer to the right, whereas tantalum makes up the layer to the left, and silicon is found throughout the sample. But it's more evident where the layers are not shading the substrate. The last sample for this session presented here is a printed microchip for SSD and CPU. The red square, the tiny red square here in the center, indicates the mapping area in the next slide. Here are EDS and WDS maps of the same close-up on the microchip sample, showing a MOSFET transistor. Silicon in green, aluminum in blue, and titanium, which is not shown here, make up the MOSFET structure. You can nicely see where the aluminum is, and it's in the same elements like the titanium, which we don't show here. And silicon, together with some, maybe together, obviously together with some other elements, is found here in between. This is the left image is showing the EDS mapping. The right image is showing the WDS mapping acquired at the same time under the same conditions. So you better see where the silicon is distributed. What you also see here is the tungsten. Tungsten indicates buried gates in the MOSFET structure. You can see these gates nicely in the WDS mapping with the red dots here. Tungsten is indicated by the red dots. And you can see tungsten in the EDS image only in this spot here where the top layer is degraded by mechanical instances. So EDS can see tungsten only in these damaged places, and is not sensitive enough to see where the tungsten is elsewhere. So WDS reveals much more details. It is much more sensitive, and therefore it can show the distribution of the buried gates of the MOSFET, which are not seen by EDS. Finally, we will have a look on two short videos. The videos are showing the workflow for WDS analysis. First, a WDS energy range scan for the element identification, and second, a WDS mapping. I will share the videos here. In a moment. Okay, okay, the video should appear here. Okay, yeah. I hope you all can see the video. So these are two videos recorded in lifetime, so there's no acceleration. It's just showing the working principle. We are starting a range scan, so we first capture an image here. This is showing the image of what was it, the tantalum silicide, showing the particles. We then decide where to do the analysis. We set a point. We could also set a field. So we indicated the spot here with the number 1. We're setting now the acquisition conditions. Up here are the ADS conditions, and down there the WDS conditions. We open the menu. We are either selecting the elements or a free range here. So we are deciding for a free range. We are setting now the energy, the start energy and the ending energy for our range scan. We are setting then the step width for the range scan and the dwell time. And all this is summing up to the total time. We are deciding then for the crystal, the analyzer crystal we want to use. We can use the help of the strategy. And we can list several jobs for the acquisition. We just start with a single job here for the one range scan. We start the acquisition. And you will immediately see the results. So EDS is acquired at the same time. Here we have the complete EDS spectrum in light blue. So it's acquired with 10 kilovolts. And we then zoom into the area of interest here of the overlap of the different lines. And you see here the range scan acquired by WDS. WDS is, as you know, energy selective. So one energy after the other is acquired. So in order to acquire a spectrum or a section from a spectrum, we have to change the inclination of the analyzer crystal. So the theta angle is changed. And what we see here is recording now of an energy range scan. We see a first peak, and we can use the finder function to identify what peaks we find here. So there's silicon indicated in red, and there's tantalum indicated here in yellow. We expect here a second line for tantalum. This should be the tantalum M beta line. And actually we see here the increase of the impulses, so the increase of the count, so the tantalum M beta line is actually there. So this is how we capture a range scan. And you see in the background, this is the EDS spectrum section, and here's the WDS range scan. We are always acquiring at the same time. Okay, we will start the second video now. This is for mapping. When starting a map, we are acquiring the microscope image. This is here the BSE image. We are then setting the mapping conditions. We can decide for a scan map or a stage map. We are setting the conditions. We're selecting the element that we want to map and the line. We can decide if we want to do it qualitatively or if we want to map the background also. We then set the time of mapping, in this case just 1 minute. We set a second element. After silicon, we now set tantalum as the second element. So 2 different energies will be mapped, and we start the acquisition here. On the upper right, you can see the WDS configurator, and you can see the energy that is currently scanned here. This is the energy of the silicon. We are mapping EDS together with the WDS. We will only show WDS at the moment. Silicon is mapped with red colors, and we see we are proceeding with a slow speed, and this is set to about 1 minute per frame. So we are mapping now for the silicon. We're seeing the particle with the inclusions where we don't see any silicon. So this is void of silicon, and we see a patchy distribution of the silicon within this particle. So we are almost done with mapping of the silicon. Now we skip the BSE image, so we only see the X-rays for the silicon. We see the patchy pattern. And you will see here the energy will be switched now from silicon to the energy of tantalum. And now tantalum is mapped. Tantalum is indicated with green colors. And the mixture will be yellow. We see the progress here. And yeah, we see an uneven distribution. We see some areas where there's pure tantalum, so bright green colors here in these spots, whereas in some areas we have a mixture of tantalum and silicon with the yellow colors, and some areas which are missing more of the silicon. Here are areas only having silicon and no tungsten. You might say this is a quite blurry image, but remember it's mapping for just a single minute. So when you're mapping for several minutes, then you will get a much clearer image. You will get much better resolution. So that's it, how mapping is done. Okay, so back to the presentation. So you should at this time be seeing the presentation again. We switch to the next slide. And this is actually the final slide. Here we already see the summary and conclusion. WDS is perfectly complementing EDS, since WDS shows 10 to 20 times higher resolution than EDS. Thus, WDS can resolve pathological EDS peak overlaps. By using WDS, we gain more information about the sample qualitatively and quantitatively. The QUANTAX WDS is especially good for low X-ray energies. It is sensitive and shows high resolution capabilities for low energies. With that characteristics, QUANTAX WDS is ideal for low voltage applications in order to resolve submicrometer structures and thin layers present in semiconductors and related microchips. That's it for today. Thank you very much for your interest.
So let's thank Michael for his excellent presentation here, and we will now have our question and answer session, which is supposed to last about 15 minutes. As we are running a little low on time, we might do probably 10 minutes. So first, a very quick reminder here, this is an interactive webinar, so you still can submit your questions through the Q&A box on the right-hand side of your screen. And meanwhile, we have had already a few questions, and I will now go ahead and ask Michael about those. And yeah, so one of the questions here is if you again could just quickly as well talk a little bit about the disadvantages as well as advantages of WDS versus EDS. Why should we go with the EDS if we have a WDS that seems to be so much better?
Well, as you say, there are advantages, but also disadvantages. So only the combination is the best solution. WDS shows a much higher resolution, as we could see here, so 10 to 20 times better resolution. That is an advantage. It also shows better peak-to-background ratios. And it's very good for light elements. However, it's energy selective, so it takes time to measure. So if you have a sample with several elements, this means measuring all the elements one after the other. So that sums up. And EDS is much faster, so you get all the elements at one glance. So maybe not that you don't see the trace elements. You have to look for them using WDS, but the major elements you will readily capture, and then that's straightforward. And yeah, the EDS is easy to use. You can do the quantification with standards like in WDS, where it's a must, but you can also do standardless quantification with EDS. Another advantage for EDS is that you do the analysis with lower beam currents in most cases. So this is good for beam-sensitive samples when you apply beam currents, which are only a few 100 picoamperes and not several nanoamps. So like for WDS, we are applying for the light elements, we would apply something like 5 nanoamps, and for some higher energy lines or elements in low concentration, we would easily apply beam currents of several tens of nanoamps. So that is not suitable for all samples. Combination. I think a combination is, with a combination of both systems, you are getting the best out of your sample.
Thank you very much. And actually, there is right away a follow-up, as you just said, standardless. So you said you can or cannot do standardless with the WDS?
So for WDS, you need standards when you want to quantify. So you cannot use the fundamental parameters since you don't have an idea of the entire spectrum. You just see a section, and to get some concentrations out of the intensities that you measure, you need to compare with a standard acquired under the same conditions. So you need standards if you want to quantify. If you just want it qualitatively, you don't need any standards. So what we have seen during this webinar was just qualitative. We did range scans. So we were just looking if the elements or the peaks were present. So therefore, you don't need any standards. Or for mapping qualitatively, like what we did, so we just set the mapping energy on the on the peak, and we mapped it just to see if the elements are present or not. So therefore, we don't need any standards. But if we would like to quantify the map, which is clearly possible, then we would need a second measurement also for the background position, not only the peak position, and we would need standards.
Thank you for that. There is here another question regarding low voltage data acquisition. You've now used 5 kV here. Somebody is asking, is it possible to go even lower, let's say 2 or 3 kV here?
Yes, for sure. That's clearly possible with the WDS also, like with EDS as well. So we are sometimes also doing analysis with 3 or 2 kilovolts. You always have to keep in mind the overvoltage ratio. So for the elements of interest in this webinar, for example, the layered sample with the tantalum and tungsten layers on top of the silicon substrate, I tried out mappings at different acceleration voltage, starting with 20 kV and going down to 10, 5, 3 kV, and this is all possible. So no matter. So we couldn't go much lower than the 3 kilovolts in that case, since we needed an overvoltage to actually see the silicon K lines and the tantalum and tungsten M lines at that position. So so therefore we stayed with 3 kilovolts. The point you have to remember is that with decreasing acceleration voltage, you also have less X-rays generated. So for a good statistic, you either need higher beam currents in that case or longer acquisition times.
Thank you for that explanation here. And here's a question, if it is possible to do actually a combined ED and WD quantification. Would you mind commenting on that a little?
Oh yes, clearly. That's a good question. Yeah, sure we can do that. So that's the only way to work with a single WDS and on the same SEM with the EDS. So we are always combining the results, and it's no problem to combine the independently acquired information acquired under the same conditions, and these information are combined to correct for the matrix effects and so on. So we are selecting single lines to be quantified by WDS, whereas the major elements or the main element inventory is determined by EDS. So we can combine all these information into a single analysis. And we can for this information or for this measurement, we can also combine not only standard-based data, so EDS and WDS standard-based, but also we can also combine EDS standardless quantification with WDS data, which is clearly standard-based. So there's no problem to combine the data, and it's working well.
But so if I understand it right, you still need a WD standard with a kind of similar composition to exactly know the intensities? Or is it possible, if you have a standardless EDX quantification, to use now a single line from WD to kind of combine that? Or do you still need somewhat a standard to translate the composition into a count rate on your WDS?
yeah, for quantification by WDS, I need a standard. So I can make my own standards. So prepare some in-house standards where I collect the information by different analytical techniques. But I need some standard to be given. So for this WDS quantification, I don't need the standard for the EDS, but I need it for the WDS.
Okay, thank you again very much. And as we are now close to 10 minutes overtime, I think we will conclude that and answer the remaining questions by email. So thanks again to Michael for the excellent presentation and good Q&A here towards the end. And as a reminder, today's event has been recorded and we will make it available for viewing very soon. And with that, thank you for being with us today, and we hope to have you with us again at future webinars. And yeah, thanks, have a great day, and goodbye.